Greetings, my name is Matthew, and in this video we're going to talk about logarithmic functions. A logarithmic function is a little unusual. However, the first thing that I think it's most important that you realize is that the logarithmic function is actually something that you've seen before, you just haven't seen it before maybe. That sounds confusing. What we see in this blue box on the left hand, well, right in the middle, but toward the left, is this statement. This is a logarithmic statement. If I read this, I would read it as y equals log base b of x. To the right of it, it says it just there that it's equivalent to this. Now, what's a little bit strange about this is normally we see y isolated on one side of the equation. And in the logarithmic equation, we do see it that way. But on the right-hand side, doesn't it almost look like the x and the y are in the wrong place, like we should swap them back? If it looks that way to you, that's good, because that's the way that we originally saw those exponential equations. Y was equal to b raised to the power of x. But here the x and the y have kind of traded places, and there's a good reason for that, and we're going to talk about it. But this ability to write logarithmic statements and these exponential statements, to toggle back and forth between the two of them, to be able to convert one into the other and vice versa, very important. You want to be able to do that. And in large part, that just means matching up the pieces. Excuse me, here we're seeing it again, just written out in a different way. And you're seeing on the left-hand side in this log statement that the base is b, and where does that base appear over here? Well, it's the thing that's holding up the exponent. I guess we could still call that the base. And to the left in the logarithmic statement, the thing that's all alone is the y value, and interestingly, in the exponential statement, that becomes the exponent. And really, x is, well, here's where it's really strange, and here's where you were right if you thought that they were in the wrong places, the x and the y values. Here, the x looks like an input value. Here, it looks like the x is an output value. And you're more right than you know, all right? So that seems a little bit confusing, but you do need to be extremely familiar with these two formats and where the different components go when you convert back and forth between the two formats. It'd be nice if there were a practice problem or two. Hey, look, there's one. Let's try to take this logarithmic equation and convert it into an exponential equation. Now, I'm going to do something that I would recommend that you do, but you're going to have to come up with your own process. But I'll tell you, I don't like the way that the question's written. The way that I relate to these equations best is if I rewrite it as log base 9 of x equals 2. I like having that non-log thing, the 2 in this case, on the right-hand side of my equal sign. It's how I standardize these problems for myself, so that in the beginning, like in this problem, if I have to make a couple little initial adjustments so that the problem looks and fits the format that I'm comfortable with, then I do that. Now I'm going to make the conversion. And here's why it's so easy for me, because I said I do it the same way every time. Here's how I read this. I start with the base, 9 to the power of 2 equals x. I draw those arrows normally in my mind, but since I'm teaching you my method, I'm drawing the arrows, and we end up with the equivalent statement 9 to the power of 2 equals x. We could go on and solve this statement. 9 squared is 81, so it appears that our x value is 81, but all we're being asked to do here is to write it in the equivalent exponential form. So this would be our answer. If the instructions involved this equation and the word solve, then your answer would be 81 or x equals 81. But in this case, we're just practicing swapping between the two different formats. Here we're being asked to go the other direction. This is sort of an exponential looking equation, but it's a cube root problem, and we're supposed to turn this into a logarithmic statement. We better turn this given equation into a true exponential statement or equation. So if you want, you can make it match this format so that it's easier to convert it from there into this format, right? You're going to have to design and devise your own process. So let's rewrite it as an actual exponential. Let's write this as 64 to the power of 1/3 equals 4. So this is the traditional exponent. This is the index on the root, or on the radical. So it's an index of 3 for a cube root. And then let's make the conversion. I don't know. It's awkward. I don't know how to do it. But what I know is the structure of what my answer is supposed to look like. So what I do is I build myself like a fill-in-the-blank problem. I know it's going to have the word log in it. I know there's going to be a base down here. I know there's going to be a larger number here. And then I know it's going to equal something. The base to the power of equals whatever this number is. Well, what's the base? The base is the number that's holding up my exponent. And that's the 64 in this case. So it's base to the power of, what's my power? I look to the left, I see the exponent, the power is 1/3. 1/3. The good news is, you should be doing this in pencil anyway. If you make a mistake, you can erase and start over again. No harm, no foul. No one will be the wiser, okay? Well, the only number I've got left is the 4. Okay, and then let's see if it worked. Base to the power of, so 64 to the power of 1/3. Yep, I'm seeing that over here. Good. Equals 4. There it is, equals 4. So it looks good. When you factor, right, if I gave you x squared plus 5x plus 4, and you want to factor this, and you say, well, that's equal to x plus 4 times x plus 1. How could I check to make sure that this is correct? So multiply it back out, FOIL, and combine like terms. See if you get x squared plus 5x plus 4. So that's sort of what I'm doing up here with these two statements. As I'm filling in the blanks on this thing, that kind of looks like a smiley face. As I'm filling in the blanks on this logarithmic statement, once I'm done filling in the blanks, then I translate this direction and see if I get the original question again. 64 to the power of 1/3 equals 4. 64 to the power of 1/3 equals 4. Yeah, I got it. Okay. So again, you've got to come up with your own process, but that's what I use. It works for me, so I'm sticking with it. Once you find what works for you, I recommend that you stick with it. Yeah, so you would type this in as a final answer without the curvy arrows. Right, so I pre-wrote these couple of things because I wanted to look at those with you before we go into the typed up stuff. The way that we were just reading and doing those conversions that we saw on the previous page, the way that I do it is I say 2 to the power of equals 8. Well, 2 to what power equals 8? 2 times itself how many times until I get to 8? 2 times 2 makes 4, times 2 makes 8. Okay, so I required 3 multiples of 2 to get to 8. So, oh, well, this must be a 3. 2 to the power of 3 equals 8. Yeah, that works. Okay. And let's try this one. 23 to some power equals 1. 23 to what power equals 1? How many multiples of 23 do I need to equal 1? Is this a trick question? Can I take a number and raise it to a power and get 1? It's not really a trick question, it's just very specific kind of a question. Remember that anything to the power of 0 equals 1. So here, 23 to the power of 0 equals 1. Does it work? 23 to the power of 0 equals 1? Yeah, that's it. Perfect. All right, so 0 would be our answer. So if I gave you this and I said evaluate, the answer to the question would be 3. If I gave you this and I said evaluate, the answer would be 0. And I could do that. I could say evaluate log base 3 of 81. Period. That could be the entire question. Excuse me. And you have to know that what you should do maybe is create yourself a little fill in the blank over there, because that's what you're searching for. You might not even be given the equal sign and the blank to fill in. You've got to write those in yourself and come up with 3 to what power equals 81. So these are very generic statements that we're seeing here. B to the power of 1 equals B. You can see why I got into mathematics. That is exciting stuff. B to the power of 0, if I nod off, somebody wake me up. B to the power of 0 equals 1. Anything to the power of 0 equals 1. All right, so no big surprises there, but realize those kinds of equations could pop up. All right, inverse properties of logarithms, because we weren't having enough fun yet. (16 to what power equals 16 to the third? Can you figure out what the question mark is? I think it's a 3, right? 16 to what power equals 16 to the 3? And the answer is certainly 3. And I have certainly made too many videos because I'm losing my voice. See if that helps. Very little. And here it is. I'm looking right here. B to the power of x equals b to the power of x. Not a big surprise. The statement below it, however, is a little strange. And actually, let me back up, because what I just illustrated for you is that this is a true statement. B to the power of x equals b to the x. Great. But what if I did this? Can I sample colors? I cannot. So arcane. What should I do? Let's just scribble this out. That used to be larger. And what if I came in here and I said evaluate log base b of b to the x? You'd have to set yourself up that fill in the blank question. Well, it's going to equal something. I don't know, b to the what would equal b to the x. I think it's supposed to be an x. And you'd be right. Okay, so that one you could use the fill in the blank strategy in order to figure out the answer. This one, a little more unusual. What's happening in this statement, however, is if you forget about this, the fact that the answer is x is a lot like this. I don't know how you would say this. The log base b and this b are kind of canceling each other out. I mean, if I get rid of those, what do I have left? Just the x. Well, what did I scribble out initially? Just the x. That's the idea of the fact that we're talking about inverse properties of logarithms, because the log mixed together with the idea of an exponent, if you set it up just right, they kind of cancel each other out, leaving you with just an x. Same thing's happening here. This b is being raised to the power of log base b of x. So in the exponent position, you've got log base b of x. And when you've got b to the power of log base b of x, it's the same thing happens. Get back there. The b and the log base b kind of cancel each other out, leaving you just with the x. All right, so you need to be aware of those inverse properties. Those are going to pop up in the occasional problem, occasional homework problem. They're not going to pop up while you're trying to put air in your tire. They're not going to pop up while you're brushing your teeth or trying to learn how to bake a cake. But in your math homework, they might pop up. Let's try some problems. Look at this. Evaluate, and then here's a logarithm with no equal sign. No fill in the blank is given to us. So I write it in myself. Equals something. I'm trying to figure out what it equals. 3 to what power equals 27? And the answer is 3 to the third power equals 27. Let's try the next one. Log base 11 of 11 equals what? Something. 11 to what power equals... Oh, I lost it. After enough video making, the iPad exercises its dominance over me. Bends me to its will. Makes me do a little bit of a reset. I have to disconnect this cable and then reconnect it and then say abracadabra, and then it comes back to life. We've got a thing going over here, me and the iPad. Where were we? Ah, yes. Let's take that back. 11 to what power equals 11? And the answer is 1. 1 multiple 11 of 11 gives us 11. All right, so the next one, we've had 3 multiples of a thing. We've had 1 multiple of a thing. Now I've got log base 6 of 1 is equal to something. Okay, let's try it. 6 to the power of what equals 1? If it equals 1 and we're talking about exponents, my knee-jerk answer is always 0. Let's take a 0, drop it in here, see if it works. 6 to the power of 0 equals 1. Anything to the power of 0 equals 1. There's that smiley face again. I've been doing this for years, never saw the smiley face. You know, if we made this turn a little bit sharper, let's do it on the next one. Log base 4 of 4 to the 6 equals something. So now I've got 4 to what power equals 4 to the 6? See what I did? See what I did there? It's like I don't have a lot to work with, right? So I've got to do what I can to entertain myself, which is tough. Trying to entertain you, even more difficult. But at least I got to draw something. That was way better than that curve that I tried to draw in the previous video when we were talking about the graph of the exponential function. That was brutal. So you tell me the answer to this one. 4 to what power? 4 to what power equals 4 to the 6? You're so smart. You don't like my heart? Criticizing me? I think that this question mark, which goes in this space right here, is a 6. 4 to the 6 equals 4 to the 6. That sounds about right. Nice. Okay, way to go. You're evaluating logarithms. I'm so proud of you. And you can graph logarithmic functions, which is that very humbling exercise, like graphing exponential equations. Check this out, though. As it turns out, does it actually say this in the text here? Yes. So logarithmic functions are inverses of exponential functions, and therefore the graph of a logarithmic function and its corresponding exponential function, which is its inverse function, their graphs are reflections of each other about the line y equals x. That's why you're seeing this beautiful curvy-wurvy flip it over kind of a thing. You're seeing this dashed line right here. That's the line y equals x. So always the graph of an equation and the graph of its inverse will be reflections over the line y equals x. When you reflect over the line y equals x, are you always going to get a function? Not necessarily. I could definitely take a very basic parabola, which is a function, and if I reflect it over the line y equals x, I get this curve, which is not a function. The graphs are still reflections of each other over the line y equals x. It just so happens that this inverse function that I drew in red right here is not a function. All right, here in blue, we're seeing the graph of an exponential function where the b value, look at the bottom of that graph, where the b value is greater than 1. So it's an increasing function, that blue curve. Its inverse function, which is small and pixelated down here, its inverse function is log base b of x. And you can see that the graph of the inverse function and the original function are reflections of each other over the line y equals x. In blue here, we're seeing still the graph of the exponential function, except at the bottom of that graph, where our b value is between 0 and 1, like 1/2, or 1/3, or 4/5, okay? So the b value is there between 0 and 1, which is why our blue curve is descending or decreasing there, getting closer and closer to the x-axis. And it's a little bit more difficult to tell that these two graphs are reflections of each other over the line y equals x, but you know, if you just grab your computer and turn it, oh, then it gets in the way of my camera. All right, so I'm not going to do that, but you could do that. Be careful, don't drop your computer. You'll see, I think, if you turn your computer at an angle, if you can, that it's definitely symmetric about the line y equals x. All right, so functions and their inverses have graphs that are reflections of each other over the line y equals x. Characteristics of the graphs of the logarithmic functions of this form. Yes. Previously, these blue graphs that you're seeing on the screen had y-intercept of +1. Their inverse functions, look at this. Look at these coordinates here, and then look at these coordinates here. It's like the x and the y traded places. Does that sound familiar? Look at this over here. Look at these coordinates. Does that look like x and y traded places there too? Sure enough. So when you're working with inverse functions, when you go from the function to its inverse, all the x and y values trade places. Every point on the blue curve that we're looking at right here, if you took its coordinates of every point on the blue curve and you traded the x and y values and you replotted them, you'd get this red curve. So by trading or swapping x and y coordinates, you end up getting the graph. The resulting graph is a reflection over the line y equals x. So inverse functions have domains and ranges that have traded places. All right, so the x-axis became, or we ended up with x-intercepts of 1 instead of y-intercepts of 1. The second bullet tells us that the y-axis becomes a vertical asymptote instead of having had a horizontal asymptote. And you can read those other two bullets. You don't need me to read to you. Now, here we are looking at transformations of the logarithmic functions, and these function very similarly. I like that we don't have those exponents that are up there. The base b is still present in these logarithmic equations in the middle column, but we don't ever tinker with the b value. We're really messing around with the x value, or sometimes we're putting a multiplier out in front. So let's just talk our way through these fairly quickly. So let's get this column in here too. So for a vertical translation, if we're adding something to the outside, it goes up. If we subtract something, it goes down, as you would think. Now, if you make those same kind of modifications inside the function, here you're adding something, it's going to move in the horizontal direction, but it's going to go in the negative horizontal direction. So be careful. You're adding something, but it's moving to the left. Or if you subtract something, it ends up moving to the right. So it's kind of backwards or counterintuitive. Here are your reflections. This stuff used to generate my y values. This negative sign is negating those y values. So if it was above the y-axis, then it becomes below. If it was below, it becomes above the y-axis. So that would be a reflection over the x-axis. If your modification happens inside, it's a reflection over the y-axis because you're negating or changing the sign on all of your x values. A vertical stretch or shrink, we're taking all those old y values and multiplying them by something. Double the y values, they get taller in the upward and downward direction. If you were to multiply them by 1/4, it would be like a vertical shrink or compression, okay? Because you're modifying the y values. X values are staying the same, y values are changing. Here, the x values get impacted in a kind of backwards way. If that c value says 3, then you get a horizontal shrink. Your graph becomes 1/3 as wide. And vice versa. If your c value there were a 1/4, your graph would become 4 times wider. Counterintuitive if your modification is happening inside the function. You start messing with that x value and things go crazy. When we looked at exponential functions and equations, we said that the domain was all real numbers because I can take a base b and I can raise it to whatever darn power I want to. Negative powers, positive powers. We raised things to the power of 0, which turned them into 1. You could raise something to the 1/3 power, which is the same thing as a cube root. So really your exponents can be anything you want, any real number. Positive, negative, 0, doesn't matter. But when it comes to a logarithm, there are some restrictions. And I like looking at it in this format. So your function, or it could say y equals, but I really like the fact that, there we go. I really like that this says log base b of g of x, because it's not always just going to be log base b of x. It won't always be log base b of a number. As you can see in question number 2, just below that, this says log base something of x plus 7. So the argument is x plus 7. It's a function, like g of x is a function. Okay, there it is. There's g of x, x plus 7. And we're being told here in blue, so it must be important, it's being kind of highlighted for us, whatever that function ends up being, it can't be anything other than a positive value. It's got to be strictly greater than 0. In other words, let's look at question number 2 here. We've got the log base something of x plus 7. I know that g of x is my x plus 7, and I know that x plus 7 is required to be greater than 0. And so if I subtract 7 from both sides of that inequality, I find that x has to be greater than -7. That's your domain. That's your list of x values that you can put into the function. It's the list of all of the x coordinates that would appear on the graph of this function. In interval notation, all the x values greater than -7 starts at -7, goes up to positive infinity, excluding the -7 with a parenthesis because we have a strict inequality here. There's no or equal to symbol. All right, so that's our domain. -7, positive infinity. C is it. Trusty C has an answer. And that may well, oh, we've got common logarithms. That's right. So up here I was saying, right at the top of the screen, I kept saying log base something of x plus 7. What's the something? Well, if you don't write anything, we assume that the base b is 10. Okay? So a logarithm function with a base of 10 is called a common logarithm. I never call it a common logarithm, but you might see it called a common logarithm, base 10. Right, so these two statements are equivalent, and it will more often than not be written this way. Just leave out the base of 10. It's assumed. What does this say? Doesn't that say the square root of 2x? And what does this say? That says the cube root of 2x. Well, this says cube root. It gets a 3 right here. This is a square root, but I don't see a 2 written there for square root. Right, it's assumed. We just know that when we see that symbol, there's this invisible 2 there. It's got an index of 2. Same thing with this common logarithm. If you don't write a base, we just assume that there's a base of 10. All right, you should know these. I wouldn't go nuts trying to memorize them, especially the first two, because we've talked about this so much. A base of 10, right in here, to the power of 0 equals 1. Well, of course it does. Anything to the power of 0 equals 1. And then the next one, a base of 10 to the first power, 10 to the first power equals 10. Yeah, duh. Most of us know that. If you don't know that, I apologize. I shouldn't have said duh. 3 and 4 are a little bit more tricky. Those ones maybe you want to commit to memory, although this one says 10 to the power of x equals 10 to the power of x. I love that one. It's really number 4 that's weird. So maybe just make put number 4 on a flashcard, make flashcards for all of them. I don't know. You got to know you. So that was the common logarithm with an implied base of 10, and then there's this thing called the natural logarithm. And the natural logarithm, if you look at this right here, has a base of e. E is back for us. When you have a log with a base of e, since it's the natural base, we call it a natural log, and it gets its own very special sort of a symbol or notation. Instead of writing log base e, we write ln, which, I never looked that up. Pause. I want to know why it says ln. I'm assuming it's like logos naturalis or something. I'm going to look it up. I'll be right back. All right, I'm going with this. I found in a post that it says that the Latin term is Logarithmus naturalis. Do you feel smarter? I feel smarter. Gotta take what we can get. So anyway, natural log is represented with an ln. We assume that it's got the natural base of e, and then we run into these properties again, which I highly recommend that you understand / commit to memory. The third and fourth ones become particularly valuable when you start trying to solve equations that have the variable in the exponent position. We're going to use e to the power of and natural log in order to get access to whatever it is that's in the exponent position. So you don't have to know what I'm talking about, just know that number 3 and number 4 in particular that I just circled on this screen, right in the middle of the screen, those are going to come in handy. All right, so hold on to those, and we have one more example. These are the notes that never end. Evaluate or simplify each expression. Right, so don't forget that, sorry, this thing jumps around every once in a while. We've got an invisible base of 10 right there. So 10 to what power equals 10 to the 8? I think 10 to the 8 equals 10 to the 8. What about this one? This is a natural log. It's got an implied base of e right there, just a little one. There's just a little e right there. Equals something. E to what power equals e? I think e to the first power equals e. Anything to the first power equals itself. What about this one? This also has an implied base of e, and it's going to equal something. E to what power equals e to the 13x? I think that e to the 13x equals e to the 13x. Do you see how if I think of it as the natural log and the e canceling each other out, that the only thing I'm left with on the left-hand side is the 13x, and there it is. On the right-hand side, it's equal to 13x. So the fact that the natural log and e to the power kind of cancel each other out can be very valuable, because now this thing, the 13x that was in the exponent position, is now, as I like to say, down on the ground, where I can get my hands on it. I could then divide both sides of an equation by 13 and really isolate my x value. So we will be doing that in the not too distant future. And lastly, this is just that weird property where just as the natural log and the e canceled each other out over here, the e and the natural log are going to cancel each other out here, leaving us with a final answer of 7x squared. All right, so for none of those did we need a calculator. For all of those, did we need to know these kind of general properties, these 1 through 4 that we saw for the natural logarithm, and the 1 through 4 above that we saw for the common logarithm. So please do build those into your study and review for this section of this chapter. And I'm pretty sure that that is the last page of notes for that section. It's going to push us into 4.3. It will. And the next time I see you in 4.3, we'll be talking about properties of logarithms. Thanks so much. See you there.